Hello everyone. This is section B of October-November 2023, Unit 5. The first question is about the electrochemical cells and redox reactions. Is asking you to draw a label diagram of the apparatus you would use to measure the standard electrode potential of Cu positive to Cu electrode with a standard hydrogen electrode include essential conditions. Okay. To draw it, you shall focus on the following things. First, we have two beakers. They have two solutions, one for copper positive 2 ion aqueous solution, and its concentration is 1 mole per cubic decimeter. That's the standard condition. And there is a copper electrode, that's Cu solid. It is attached with voltmeter, and this one is attached with platinum electrode that is connected with hydrogen ion solution, and its concentration also 1 mole per cubic decimeter. And here we have a current of hydrogen gas, which is at 100 kilopascal, and there is something which is very important also, which is the salt bridge. This is the salt bridge. Okay, and you shall know that the temperature is 298 Kelvin or 25 degrees, which is the room temperature. So there you shall include in your diagram all these things. That's very important. Now, what's next idea is, what's the coming next is this reaction or this question. The standard electrode potential for the two half cells are shown. Okay, you will see the dichromate was changed to chromium 3, and this is a reduction, and its electrode potential is positive 1.33 volts. For Cl2 plus 2 electrons, it's 2 chloride ions. The electrode potential is 1.36 volt. Explain in terms of the electrode potential why the acidified dichromate ion reacts with concentrated hydrochloric acid to form chlorine, even though that the E cell is negative 0.03 volts. You have 3 marks for this question, and this is abnormal idea. Okay. First of all, since the E cell is negative value, this is identify the non-spontaneous reaction. But he made the concentrated hydrochloric acid as bolded term. Now, this means that concentrated hydrochloric acid, where you have concentrated hydrochloric acid, concentrated hydrochloric acid, HCl solution used, this increases the H plus AQ in the right side of first equation. Okay? Since the equilibrium there is shifted to the right. Okay? This will shift the first equilibrium to the right. This makes E naught for the first reaction greater than 1.33 volt. And if there is more Cl negative ion in the second one, this means that the reverse reaction will be increased. So this means that where more Cl minus, this leads to more concentration or more concentrated ion in the second equation or equilibrium. Okay? So, can write more. So, this makes the E naught for second reaction greater, this makes lower than 1.36 volt. So, since the first one is greater than 1.33 and the second is 1 lower than 1.36, so the difference will be more. So this makes the E cell more positive, since there is a small difference in E, or between the E naught for both electrodes. Briefly, if you increase the positivity of the first one and you decrease the positivity of the second, this will make the difference more positive. That's why it's a feasible reaction by the addition of hydrochloric acid. Now, he's asking you to write the cell diagram using the conventional representation of the half cells for the reaction to produce. You know, there is a specific way to write the E-note cells. So this is where the two lines here was used for the salt bridge, and you shall identify the platinum electrode where the 2 or 2Cl AQ, when it state symbols, was changed to Cl2. And for the reduced one, this is the platinum electrode, and it is identified by line like that, and it's in solid. Then we have the dichromate Cr2O7 negative 2, that is changed to Cr positive 3, and we have also Cr2, we have in the presence, here we in the presence, wait, since we have a hydrogen ion, so this is Cr2O7 negative 2 AQ. In the presence, we can take the notation from the equation. Here we have 14 hydrogen was changed. We have also 14 hydrogens, and that's the left side of the equation. In the acidic form, there is a comma, and the products are 2Cr positive 3 AQ, and we have water, 7 water molecules. We have 7 water molecules, and you shall close the the brackets, and we have platinum solid electrode. That's the way how to write the notation. Let me tell you most important things for the salt bridge. This is the electrode, or the left electrode, where the oxidation takes place, and here the reduction. And after this salt bridge, we write the equation and the electrode, and at the end we have the electrode. Okay? That's how to write the notation. Now, for the next question, when a 25 cubic centimeter of 0.1 mole cubic decimeter of the solution X2O5 reacts with a reducing agent X, it is reduced to the lower oxidation state. To oxidize X back to its original oxidation state requires 50 cubic centimeters of 0.2 mole. So he gave you the concentration and the volume of the solution which is used in the titration, which is potassium manganate solution. And according to the equation, calculate the oxidation state of X after it has been reduced. Okay, here we have 3 marks. So we can find the answer like that. First, you can find the moles of MnO4 solution, which is the 50 over 1000. It's the volume times the concentration, which is 0.2. And this will give us how much? It will give us 0.00 1 moles, and you can find the relation now. This is for the what is used. Now, in the first or in the beginning of the question, he gave you that 25 of X2O5 was used. So we can use these two numbers, the volume and the concentration of the original solution. So the moles of X2O5 equals 25 over 1000 times 0.1. That's equals 2.5 or 0.0025 moles. After that, you can find the ratio between X and, so the moles of X there and the moles of X there, can find that. Now, moles of X equals 2 times, this is can be written 2.5 times 10 to the power negative 3. So it is 2.5 times 10 to the power negative 3. This equals 5 times 10 to the power negative 3. Now you can find the molar ratio between MnO4 negative 1 to X. You will find that the ratio is 5 to 1. What does it mean? Now, if you return back to the equation, you will find that we have 5 electrons was used there. This means that since the ratio is 1 mole to 5 moles, this means that only in X2O5, the original oxidation state is X positive 5. So it is changed to X what? Since it is 1 to 5 ratio, this means that we multiplied the equation of the reduction of positive 5 to the lowest oxidation state, we multiplied its equation by 5. So to make the ratio 5 electrons to 5 electrons, this means that the oxidation state is positive 4. So this means that in the original equation, only X5 was changed to X4, okay, plus 1 electron. So 1 electron was added, so the oxidation state is X positive 4 after the reduction takes place. Okay, now for next question, this equation is about compounds and complex ions of iron. A compound of iron contains by mass 39.5% and 28.2% of iron and 32.3% of oxygen. Calculate the empirical formula. So to find the empirical formula there, you shall find the percentage or the number of moles of each element. So we can start by the percentage of each element, which is iron. And we have, iron contains, iron by mass 39.5%. And here we have for potassium, we have 28.2%, and oxygen, it's 32.3%. Now, you can convert them into mass. So you can consider this as grams in 100 grams, or suppose that it's 100 grams of the molecule. Now to find the moles of each element, you divide over AR, or the relative molecular mass of each one. So you will find 39.5 over its molar mass, which is 55. We can consider the periodic table in the data booklet or in the paper itself. And for oxygen, it's 32.3 over 16, and for potassium, it is 20. It is wait. We have a compound contains 30 of potassium. We flip them. So wait. So I must say, wait. So it is. So this one is for potassium, okay, which is 39.5 over, it is 39.5 over how much? It is 39.1, and the answer is 1.01. Now for iron, it's a 28.2, and its moles equals over 55.8. So this equals 0.505 moles. And for the next one, it is 2.02. Now, the ratio is 1. You can find the ratio between these numbers by dividing over 0.505. So the ratio between K to iron to O is, it's 2 to 1 to 4. So it's K to FeO4. That's the formula, right? Now, what's next is asking you the reaction between iodide ion and persulfate ion is thermodynamically feasible under standard conditions, and the reaction is very slow, but it is catalyzed in the presence of iron positive 2. So you can see, give a reason why the activation energy for this reaction is high in the absence of the catalyst. As you can see there, you have two negative charge species, which they are iodide and -2 and -1, which they are two negatively charged ions. They repelled So you need much more energy to overcome the repulsion force between two negative charged ions. Now to write, so more energy is required to overcome the repulsion between two same charges. Okay? Now, write the equations for the reaction between that occur when the catalyst of iron positive 2 is added. State symbols are not required, so we can write these two equations, okay, by referring back to the paper itself there. So that's the paper here on my phone. So it will be like that, 2 Fe positive 2 plus the first reagent is thiosulfate. No, it's 2S2 negative 2. It goes to 2Fe positive 3 plus 2SO4 from the original equation. And you will see that 2Fe positive 3 plus the second reagent, which is 2I minus, give us 2Fe positive 2 plus the second reaction, which is this. As you can see there, the iron positive 3 is intermediate. That's why we started within this one and finished with the other. Now, in aqueous solution, iron 2 exists as a complex ion for Fe. Now, next idea is, in aqueous solution of iron 2 exists as a complex ion FeH2O by 6 positive 2, saying how the water acts as a monodentate ligand. Okay, to explain this, the term mono means one, dentate, so it can share pair of electrons, or it can do only one dative covalent bond. Okay, so the answer is it can share one pair of electrons to do one dative covalent bond. Okay? Now, what's else? Explain the shape of the iron, the shape of iron positive 2 hexadentate complex ion. Since where the coordination number is 6 for this one, it will be tetrahedral, and tetrahedral because it will share 6 electrons, so you have 6 pairs of electrons. There are 6 pairs of electrons, and so it is like the shape of the molecules in AS chemistry. You can explain it according to minimize the repulsion Vesper theory. So because there are 6 pairs of electrons around the central iron positive 2 ion or transition metal ion. This means that the shape is octahedral, and that's to minimize. You can see there are 6 pairs of electrons. It's octahedral, and to minimize the repulsion between cis bonded pairs of electrons around the central atom. The next important point is to minimize the repulsion between 6 bonded pairs around the central atom. You will see this is the correct answer, and that's what is needed. Next question is, or next part of this question, the hemoglobin is an iron 2 complex which carries out oxygen around the body. Part of the structure of oxyhemoglobin is this one, where the polydentate or didentate globin is this one. The 4 nitrogen atoms are part of the multidentate ligand in the heme group. Explain in terms of the iron 2 complex why the carbon monoxide is toxic. Okay. Now you will see that the carbon monoxide is toxic because it will react, or it will enter the hemoglobin, and it will replace the oxygen in the molecule, and it will bond strongly with the with the iron positive 2. So if you return to the structure, you will find there is an oxygen there which can be replaced by CO2. So since CO2 molecule can replace or replaces O2 molecule, and it is bonded strongly with Fe positive 2 in the molecule of hemoglobin. That's why it's a toxic gas. Now, for ethane diweight ligands reacts with iron 2 in aqueous solution, explain in terms of the entropy why this reaction is feasible. You can see that we have 3 moles of particles. They are changed to 5. So in this case, we are looking at the number of molecules or moles of particles. They are 3 moles there. But here we have 4 and 1. They are 5 moles. So you can explain that according to we have more number of particles, okay, and the delta S of the system increases, and this makes the reaction more thermodynamically or more feasible reaction. So since the number of particles increases, this increases the delta S for the system, or it makes it more than zero or more positive. That's why the reaction is feasible. Okay. Now, for this part, potassium dichromate 5-oxidize the iron 2 ion to iron 3 ion in the acidic solution, Cr2O7 plus 6Fe positive 2 and 4H2, 2 chromium and 6 iron positive 3. The iron 3 ion does not react with acidified potassium dichromate. Solution Y contains 6.02 grams of iron as a mixture of iron positive 2 ion and iron 3 ions. Here we have 50 cubic centimeters of dilute sulfuric acid is added to 25 cubic centimeters portions of Y, and it is titrated with a solution of 2.56 grams of dichromate ion, and the titration is repeated until the concordance results are obtained. The mean titer of the dichromate is 22.55 cubic centimeters. Then he's asking you to calculate the percentage of iron positive 3 ion. Let me summarize the story there. The idea is, because first of all, you shall know that iron 3 ions will not react with the acidified potassium dichromate. So at the end, you can find its moles and you can find what is the mass. A solution Y contains 6.02 of iron as a mixture of iron 2 and iron 3. So this solution contains both ions and 50 cubic centimeter, and this of solution Y. So this means that we have this number of moles, and with a solution containing 2.56 grams of dichromate ion, and the titer is. Now we can convert the concentration into moles, and starting from the value of the dichromate ion. So the first step is to find the concentration of dichromate ion. Can see. First step is to find the dichromate, the concentration of dichromate which is Cr2O7, Cr2O7 negative 2 solution. Okay, we can find it in mole per cubic decimeter like that. If you take 2.56 over its molar mass, which is 216, this will give us 1.1852 times 10 to the power negative 2 mole per cubic decimeter. Now, the moles of Cr2O7, the dichromate solution, equals the volume, which is 22.5 over 1,000 times the number of moles that we found. This equals the 2.6726 times 10 to the power negative 4 moles. Now, you can find the mole from the equation, the mole of Fe positive 2 equals the moles which we found, 26726 times 10 to the power negative 4. According to the molar ratio, it is multiplied by 6, which equals 1.6036 times 10 to the power negative 3 moles. Now, this equals, okay, if you convert it into mass, this equals 1.6036 times 10 to the power negative 3 times the molar mass of iron, which is 55.8, or you can consider it 56. It is awarded answer. So this will give us a 3 point, this is, okay, since it is multiply the mass of iron, it is in 25 cubic centimeters, okay, this is 55.8. First of all, we found the number of moles of this, and here the mass is 55.8 over the 25, okay, since it's the volume of the solution, okay, and this equals what, times 1,000, sorry, here we shall multiply it by 1,000, 55.8 times 1,000, since to find its moles over, this is the moles, okay, in the concentration times the molar mass, this equals 3.5791 grams, okay. Let me clarify this. This is the number of moles that found in the titration. He's asking you how much in the 25. That's why we did this step. And after this, we shall find the mass of iron positive 3, which is the original mass that is not reacted. He said that iron 3 was not reacted. So equals the original mass, which is 6.28 minus 3.5791. That's equals to 2.7009 grams of iron positive 3. Now, the percentage is equals 2.7 0.09 over the 6.28. That's the percentage of iron positive 3 times 100%. That's equals to 43.007%. Okay, so let me summarize. That's what we have. We have, first of all, we found the moles of the dichromate which is used, molar ratio to find the moles of iron positive 2. Then we found the mass in 25, and then we convert the mass of iron 3 which is left, which is unreacted. Then we divide over the original mass, which gives you the percentage of iron. Okay, here I will stop there, and I will continue within the coming video.